So this is the first lesson from chapter 7, which focuses now on what we call exponential functions. And what you see are a bunch of exponents. And so we're going to start by reviewing some exponent laws. But really, we've been dealing with exponential functions informally in the last section. As we'll see, every geometric sequence you dealt with was a type of exponential function. So what's the difference between what we call an exponential sequence and an exponential function? Sorry, a geometric sequence and an exponential function, I'll get to shortly. First, let's review various exponent laws that go back to grade 8 and up to grade 10. In general, right here, multiplying two powers of the same base, you can just add your exponent, same as x to the power of a plus b. If you're dividing powers of the same base, you can subtract your exponent, same as x to the power of a minus b. And keep in mind, for all of these, you can look at these either way. Right? Quite often students look at this like one directionally going from here to here, but you can also look at it this way. For all of these, you can rewrite exponential expressions in many, many ways. That's it over here. If I have one power raised to another, that's the same as one power multiplied by the other. So x to the power of ab. If I have multiple factors all being raised to the same power, if I want, I can rewrite each of those factors to that one power. Quite often we kind of imagine it looking like this, although we're not distributing in A. But again, if you have multiple factors all raised to a power, you can write them individually to that power. And if you're dividing factors to the same power, you can write them as each of those factors being raised to that same power. Essentially, that's grade 8 and 9 right there. Going into grade 10 is what a power of 0 is. Anything to the power of 0 is 1. As long as x does not equal 0 itself. Essentially, a power of 0, you can think of it as meaning a number divided by itself. So again, 5 to the power of 0, you can think of it as 5 divided by 5, which is always going to be 1. And so as long as your base is not 0, which we'll never deal with, anything to the power of 0 is 1. What about negative exponents? Really going into grade 10 here, a negative exponent means repeated division, whereas a positive exponent means repeated multiplication. So in this case, I can think of this as 1 divided by x a times. So x to the power of a. And in practice, we notice negative exponents are equivalent to positive exponents in the denominator. What if you already have a negative exponent in the denominator? That's the same as a positive exponent in the numerator. And what if you have multiple factors all being divided to the same or being multiplied to the same negative exponent? Well, in this case, I can rewrite each of these individually to that power and then combine that with what we just saw. I can rewrite both of these as positive exponents. So x to the negative a is same as x to the positive a in the denominator, and y to the negative a in the denominator, same as y to the positive a in the numerator. And lastly, again, just going back to grade 10, when you have rational exponents, so a fraction near exponent, it's a combination of a power and a root, a radical. And so in this case, I can write this as x to the power of a, and then finding the bth root of that. Or it's the same as the other way around, x, finding the bth root of it first, and then all that to the power of a. They're exactly equivalent. All right. And so keep in mind all of these things are review. Some are probably come back to you faster than others, but we're going to work with exponents constantly, so we want to remember these things. All right. So what's a basic exponential function? 2 to the power of x. Okay. It's not it's, in my opinion, this is the simplest exponential function. And so first, let's think what this looks like. If you replace x with these values, especially if you don't decimalize them, it makes the pattern more obvious. But if you decimalize them, it makes it easier to graph. But x to the negative 1/3. Sorry, I take that back. X to the negative 3. Oh, sorry, it's morning. 2 to the negative 3, take 3, is the same as 1 over 2 to the positive 3, which is 1 over 8. So 1/8. Now, for graphing it, decimalizing it's probably more useful, but this will kind of create a nice little symmetrical pattern here. 2 to the power of negative 2, same as 1 over 2 squared, or 1 over 4. This is 1/2. This is 1. Remember, anything to the power of 0 is 1. And then 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And so notice this nice sort of symmetry here between negative and positive exponents. They're reciprocals of one another. That's it for graphing. Let me graph these points. So I'll start with when x is 0, y is 1. When x is 1, y is 2, 4, 8. And then the negative. When x is negative 1, y is a half, and then a quarter, and then an eighth. And at this point, it's getting tough for me to be much more accurate than that. Now I must realize that no matter what, I can see as x is getting more negative, my y coordinates are getting closer to 0, but they'll never equal 0. I can't take 2, raise it to a power, any power, and get exactly 0. Because again, a negative exponent means repeated division. I don't care how many times I divide by 2, I'm never going to get nothing, but I'll get really, really close to it, which lets me know there must be a horizontal asymptote right here, right along the x-axis. And then we can get the sense as well as x is positive. The larger x gets, the larger this, the higher y gets at an increasing rate. And that is the sort of the basic characteristic of an exponential function. So let me kind of draw my curve now. Then I'll mention what makes this different from a geometric sequence. So there's not much different between this and a geometric sequence. That's it. There's my graph of y equals 2 to the power of x. So what's the really only difference between an exponential function and a geometric sequence? Two main differences. An exponential function doesn't have a start. For example, this graph goes forever to the left. There's no starting point. I mean, you can imagine 0 being the start, but the graph doesn't have to start there, whereas a geometric sequence always has a starting point. That's the one of two differences. The only other difference is that this is continuous. This is not a series of points. This is a continuous curve. A sequence is always discrete, we call it. A sequence is always a series of terms. But that's it. And so, like I said, we've been dealing with exponential functions informally for several lessons now. And so that's it, 2 to the power of x. The domain is all real numbers, including 0, right? You can put any number you want into an exponent. The range, though, as we can see, is always going to be just greater than 0. Unless you start adding other transformations, all exponential functions will behave like this in terms of having a range greater than 0. All right, so this is an example of what we call exponential growth. If you look at the graph from left to right, which is the convention, it's getting larger. And especially as soon as we pass 0 on the x, it gets larger at a rapidly increasing pace. And becomes, for example, by the time I get to just 5, 2 to the power of 5 is 32. But by the time I get to 10, when x is 10, 2 to the power of 10 is 1024. And so, the scale of my graph, if I want to show more, I'd have to start compressing the vertical scale a lot, and we'll have to do that a lot. All right, what about 1/2 to the power of x? When a base is less than 1, which means every single time I multiply by x, it gets smaller. I'm repeatedly multiplying by a half. Well, if you put the same values of x into here, you'll get the same values of y out, just the other way around. For example, 1/2 to the power of -3 is the same as 1 to the -3 over 2 to the -3, which is the same as 2 to the +3 over 1 to the +3, which is 8. And so, if I do the same thing for all the rest here, 1/2 to the -2 is going to be 4. 1/2 to the -1 is 2. 1, and then I get 1/2, 1/4, 1/8. I get the exact same values I had before, just the other way around. And so I know what the graph is going to look like. It's going to look the exact same as before, but the other way around. And so I'll start by graphing these points, and then I'll graph these points. And so I know there's going to be, again, that horizontal asymptote. And it's the exact same curve as before, but just reflected horizontally. So if we look at it from left to right, the graph is decreasing. It's decaying, we call it. And so we call this an example of exponential decay. We call this an example of exponential growth. With that said, algebraically, we can also see that this graph here must be a horizontal reflection of this graph. And I can show that right here quite quickly. If I write 1/2 as 2 to the -1, which again, remembering what a negative exponent means, which was just reviewed, 2 to the -1 means dividing by 2 once. That's what a half is. And now I have 1 power raised to another. When you have 1 power raised to another, you can multiply them together. So this must be equivalent to 2 to the negative x. And notice the only difference between this and 2 to the power of x is that negative in front of the input. That is, as we learned on like day 2 of this class, a horizontal reflection when compared to y equals 2 to the power of x. So without even graphing it, I could see that this must be a horizontal reflection compared to 2 to the power of x. That's it. Domain and range are the same as before. Oops. All right, so these are the 2 basic exponential functions, decay and growth. And so let's kind of summarize this right here. In general, if I have an exponential function with a base of c, well, depends what that c is. Now, I will say for an exponential function to be an exponential function, your base has to be a constant. The variables in the exponent, the base must be a constant. So something like this, x, well, that's a weird looking x, eh? Let's try that again. X to the power of x is not an exponential function. It's a mix of things because the base is also changing. So to be an exponential function, the variable has to be in the exponent, the base must be a constant. And so really what matters is one of 2 possibilities. What if the base is between 0 and 1? If the base is between 0 and 1, that means you're repeatedly multiplying by a number that is making your output smaller and smaller and smaller, like the one we saw before with a half. And every time we have something like that, we'll always have a horizontal asymptote on the x-axis. It'll always cross the y-axis at 1, but it's going to decay, so it'll always look something like this. And we call this exponential decay, like I mentioned before. And I don't care where the number is between 0 and 1. It's always going to behave something like this. You know what? Maybe it's actually good if I switch to Desmos here. I'll talk about this one later. Let me just graph y equals, I don't know, 0.1 to the power of x. OK. It looks like before. If I change this to 0.2 to the power of x, 0.3, 0.4, 0.5, even if I get really close to 1, like 0.99. OK? You may think that looks profoundly different from what I had before. But if I compress one of my scales again, you can see in the end, let me turn that graph off, it's behaving all in the same way. Yeah, my scales are different, but it's the same type of behavior. And so similarly, if I make this anything more than 1, like 1.01, it looks like growth. And if I make it, I don't know, 20 to the power of x, it looks like a right angle. But if I just zoom in more, you can see, again, it's always, I can bring it back to that same sort of shape, that same sort of distinct shape. That's it. Let me summarize these things here. And so if c is greater than 1, it's growth. But again, horizontal asymptote in the same place. Same y-intercept, but growing instead of decaying. And when people talk about something, you know, growing exponentially, like a virus, it always has this sort of feature of, for a long time, not seeming to do much, and then suddenly starts to grow kind of out of control. All right, so what if the base is exactly 1? I'm going to show you in Desmos in a second, but you don't really need to. In fact, you know, I'm not even going to show you in Desmos because we don't really need to. If the base is exactly 1, then my equation is y equals 1 to the power of x, which just means 1 divided by itself or multiplied by itself repeatedly, which is always going to be 1. And so this is the graph of just y equals 1, which is a horizontal line. It's not exponential. So if your base is 1, it's not an exponential function. It's a horizontal line, and there's nothing more to say about it. It's just a horizontal line at 1. What if your base is negative? Then things kind of fall apart. In fact, let me show you. Let's, you know, all these things, no matter what I made this base, you know, if I make it 2/3, you know, it still has that sort of exponential, in this case, decay. If I make it 0.002, and I compress it enough, you can see, again, this is that same sort of exponential decay in this case. What if I make it 0? What if I make it negative something? -1. There's nothing. And that's because as soon as my base is negative, everything kind of falls apart. You know, if my base is not negative, x can be any number. You can replace any number in, and you get this continuous curve. As soon as your base is negative, I can't put any number into this. Why is that? Well, let's just kind of see. Let's pick it. Let's go back with -1 to the power of x. Let's say x is I don't know, a half. Okay, so -1 to the power of a half is the same as the square root of -1, which is an imaginary number. It's not even a real number. And so when x is a half, we can't graph that. But when x is 2/3, x to the -1 to the 2/3 is the same as -1 squared and then cube rooted. This time you can, because -1 squared is +1. The cube root of +1 is 1. And so, depending on some numbers, you can actually get an output. Some you can't. And again, it's completely different from what we had before. It's no longer a continuous function. Hence, Desmos doesn't really show you much of anything. So, long story short, it's not an exponential function. And so we don't deal with it. So if c is less than 0, then y equals c to the power of x is not a continuous function. I'm not saying you can't substitute some values in, but you can't substitute others, and which is, again, very different from everything else. The domain of exponential functions otherwise is all real numbers. So long story short, an exponential function, everything we're going to be dealing with for the remainder of this course, only makes sense but if your base is a positive number that's not 1. A positive number, not 1. All right. Let's get to the final problem. So what I have here is an example of exponential decay. And this is something called half-life, which we'll hear about a bit. And you've probably heard about it from, I think it's chemistry. But as it says here, if a substance is radioactive, that means that the atomic structure of the substance is unstable. And over time, atomic particles escape, causing the substance mass to decay, to get smaller. And a measure of how quickly a substance loses its mass is called half-life. And although this is not a chemistry class, you are expected to know what half-life means. And half-life is a measure of the time it takes for some substance to lose half its mass through radioactive decay. So how long it takes to lose half its mass. And so what I have here is a half-life graph, or a graph for the decay of this iodine 131. Okay, and you can see, for example, at the start, at time 0, at the bottom we see elapsed time. Time 0, there were 100 grams. By the time we get to day 80, there's only 0.1 grams left. It just decays on its own. All right. So what's the question first? Well, first, what is the half-life of iodine 131? And again, half-life is a measure of how quickly a substance decays. And so I'm looking for, in the end, it's a measure, it's a number. And so what is the half-life of iodine 131? Look at my graph. Really, I want to see, okay, it started at 100 grams. It doesn't really matter what it started at, though. The key is now, how long does it take to get to half of that? So half of 100 is 50. And so to get to 50 grams, it takes 8 days. So the half-life of iodine 131 is 8 days. And even if I started with 1,000 grams here, then this would be 500, and it would still take 8 days. So it doesn't actually matter what the initial mass was. The half-life is always going to be the same for a particular substance. All right, here's the main question. Determine an equation that models the mass after t days. So, for example, let's say I change this. Let's say this was 1 day, 2 days, 3 days, 4 days, 5, and so on. Then an equation that models this would actually be pretty simple. If I wanted m to stand for the mass, here I have percentage, but I guess, oh yeah, it's percentage, not mass. Whatever. Oh yeah. You know what? I never actually noticed the scale of this graph says percentage, not mass in grams. You know what? Let's just pretend it says mass in grams. It doesn't actually matter. But for the next question, let's say this, mass in grams. Oh no. No, it doesn't actually matter for the next question. Ignore me again. Yeah, just ignore me. In fact, just ignore me the entire time. Just turn off the video, walk away. But if you're not doing that, I'll continue. And so back to what I was saying. If we had, I forgot, it says right here, the mass remaining of a 50-gram sample. So I'm telling you if this was 50 grams, and every day we lost half the mass. Okay? So again, what I'm doing is simplifying this for a moment and pretending it takes 1 day to lose half the mass, not 8. Then define the mass after t days would be relatively simple. The mass would be 50 grams, because we start with 50 grams, times a half every day. So on day 0, it's just 50. On day 1, it'd be 50 times a half, which is 25. On day 2, it'd be 50 times a half twice, which is 12.5. And so in general, again, if the half-life of iodine-131 was every day, not every 8 days, this would be the equation. So let's write that down first, even though that's not what the answer is, but it's very, very close. And it's close enough that I'm actually going to write down. So the mass would equal 50, the initial amount, times a half, which again is from the fact that it's a half-life, every day. So again, please, this is not correct. This is if the half-life was every day. Well, what's the only difference now? It's not every day. It takes 8 days. So everything I just said down here takes 8 times longer. So if I look back at my equation here, 50 won't be cut in half until t equals 8, not till when t is 1. So how can I take that into account to my equation? All I have to do is take my t and divide by 8. Now notice that when t is 8, after 8 days, 8 divided by 8 is 1, and we will multiply by 1 once. When t is 16, 16 divided by 8 is 2, and 1/2 to the power of 2 will cut 50 in half twice. And so this also works for all the days in between. When t is 4, halfway before the first time it's cut in half, t will be we'll be able to find the mass by 150 times a half to the power of a half, the square root of a half. And so this here, that one little change, allows me to take into account that it takes 8 days for the half-life, not 1 day. And that's the main part of the question. And we have an exponential model here that covers the graph you see above. Okay, and this in particular for a 50-gram sample. All right, I apologize for those mistakes from before. That said, the last question is using this. So now that we have this model for the mass of iodine-131 after any number of days, how long will it take for the mass, that 50-gram sample, to go down to 10 grams? Which means I want to make 10 equal 50 times 1/2 to the t over 8. So how could we solve this? Well, one thing you could do is divide both sides by 10 or something like that, and you would get, or divide both sides by 50. Either way, though, you've got this t in the exponent. And again, really to solve this algebraically, we have to use logarithms. And again, logarithms we'll get to in a few lessons. But until then, I can't have us solve this algebraically, but we can solve it graphically. And so in this case, to solve this graphically, which is the same idea we've seen throughout the course, solve anything graphically, one common way of looking at it is to graph the left side of your equation and the right side of your equation and see where they are equal to one another, to where they intersect. And so that's what I have kind of set up here in Desmos here in a moment. So let me close this. So what I first have up here is the equation for the half-life, where y is mass, x is time. And so if I adjust my scales now, notice I'm compressed. Oh, let me turn that on. That helps. There we go. Compress my y scale. And there's a nice sort of graph of how this sample is decaying. I now want to see how long it takes to get to 10 days, and so I just want to graph one more equation where y equals 10. And right there is my solution. So it'll take a 50-gram sample about 18.5 days to get to 10 grams. And so if you want to solve that algebraically, it's not long at all. In fact, in the end, once with a bit of practice, it'll probably be faster than getting out Desmos and typing in the two equations. But it's going to take me a few days to get there. So for as of now, I want you to understand the idea about how the graph of these equations can help us solve some of these. All right? Although, to be really honest, the most important idea of this was how to get this equation right here. And we'll have more time with that. All right. Sounds like I should stop talking. Good idea.